Now, if two events are independent, it means that the probability of one happening is not affected by the probability of another happening. So, for example, if you're in a country that it rained a lot and you looked outside and the weather was quite poorly, it was cloudy, it looked like it could rain, then that would affect the probability that you took an umbrella with you. So those events would be dependent on each other. Independent is when the two events do not influence each other whatsoever. Like if the probability that someone likes football is 0.7 and the probability that someone likes maths is 0.4, those two events are clearly independent. Just because someone likes football doesn't automatically mean or affect whether they like maths. Okay, so those events would generally be independent of each other. And this brings us to another formula. So when two events are independent, the probability of the events happening is just the two events multiplied by each other. So when I was talking about that football and maths one, I said, what did I say, 0.6%, so 0.6 like football, 0.4 so like maths, and all I would do is multiply these together, okay, because they are independent. However, if they're not independent, then this formula does not work. It's only for independent events. Okay, it's a different formula if you've got dependent events. So just thinking of this one and the one before it, these are the type that you did in Key Stage 3. Okay, but obviously now you moved on and you've got to think about things that are, dependent on each other. Often, when we have things that are dependent on each other, so not independent, they're often shown in tree diagrams because you follow the tree, this event happens and then it affects what happens next. So often they are tree diagrams, but not exclusively. They could still be in a Venn diagram. So this is what we're looking at. Mutually exclusive is or, and you add, which is written like this, the union, but only this formula is only for mutually exclusive. Independent is and you multiply, and again that is intersection, but only for independent events. So in this example, we have a Venn diagram, and it shows the number of students in a class who watch any of three popular TV shows, A, B, and C. Part A, find the probability that a student chosen at random watches B, C, or both. So we are looking at the probability of B, or C, or both. So that's going to be essentially these four values. Because this is watching B, this is watching all of C, but obviously we don't include those 10 people twice. So it's B, this is both, this is B, this is C, this is both. Thinking of it that way. But essentially this is all of B, this is all of C, but we don't want that twice. So it's this, and this. So we've got 4 plus 5 plus 10 plus 7. And that's over my total, which is 3 plus 4 plus 5 plus 10 plus 7 plus 1. And that gives me 26 over 30, or 13 over 15. Now, part B is determine whether watching A and B are independent events. So for this, we need to think about that the probability of A intersection B is equal to the probability of A times the probability of B if independent. And I do like to put that down when I start to work this out. So we need the probability of A. So the probability of A is here, so it's 7 over 30. Probability of B is the circle for B, so it's 19 over 30. And the probability of A intersection B is where the two intersect, so it's 4 over 30, or 2 over 15. Now let's go and work out our values in terms of our A times B. So probability of A times probability of B is 7 over 30 times 19 over 30. So over 900, and that gives me 133 over 900, which doesn't simplify. And since it doesn't simplify to give me this, they are not independent. So we can say, the probability of A intersection B does not equal the probability of A times the probability of B. Therefore, watching, and this is where you just take it from the question, watching A and watching B are not independent events. So watching A and watching B are not independent events. So what that means in the kind of real world terms is that the people who watch A or watching A has an impact on watching B or vice versa. It means that it has an influence on each other, and that's why they're going to be not independent. Now, before we do go on and give you at least one go here, we didn't talk about mutually exclusive, but if you look here, events A and events C are mutually exclusive as they do not overlap. Okay, so they don't overlap, so these two events are mutually exclusive. So for example, the probability of A intersect C would be 0. This is often referred to as the empty set, and the empty set looks like that, has a line through it. Okay, so the probability of any kind of empty set is 0. So, easy question, got a Venn diagram, bricks, action figures, trains, state with a reason which two types of tie are mutually exclusive. So, mutually exclusive is going to be bricks and trains. Reason, they are circles do not overlap, or they do not overlap. So it's not really a circle, is it? But yeah, anyway. Part B, determine whether or not the events plays with bricks and plays with action figures are independent. So probability of plays with bricks is going to be 4 out of 21. Probability of F is going to be 6, 10, 11 over 21. And probability of B intersection F is 1 over 21. So if independent, probability of B intersection F will equal probability of B multiplied by probability of F. So probability of B times probability of F is 4 over 21 times 11 over 21. And that gives me 44 over 441. So they're not independent. So probability of B intersection F, therefore, does not equal that. So events are not independent. Simple as that. Next, we're going to very briefly just mention conditional probability. This is something we've already talked about within Venn diagrams, and it's when the probability of an event happening given that another event has already happened. So in terms of some formulae, for independent events, the probability of A given that B has happened is actually the same as the probability of A given that B has not happened, or just the probability of A. But this is only for independent events. Sorry, I had a brain freeze on spelling independent then. Equally, I can write it the other way around. Like so. And this can be another way of showing whether events are independent. So just like the last one, when you can show that the, say, A intersection B is equal to probability of A times probability of B for independence, you can also use this to show independence as well. Okay, so that's what I'm showing you now. But since we've already kind of talked about it in terms of the Venn diagrams, I won't do that. But what I will do is maybe just a very quick example from a two-way table, and then we'll move on. So here's a two-way table. You would have seen them in your IGCSEs or GCSEs. They're quite straightforward. The likelihood of seeing one, I think, is quite slim in the exam. Like I said, given the way the previous ones have gone for P1 and P2, but you never know. So very straightforward. Find the probability, in this case, first one, of a year 10 student. So you look, right, I've got 29 year 10 students, and that is a total possibility of 30 students. So, 60 students. So it's 29 over 60. Now, part B is probability of a curry given it's a year 10 student. So what that means is now we're locked into just the year 10s, because it's given that it's a year 10 student. So we're locked into the year 10s, 18 like curry, and we've got 29 year 10 students. So 18 over 29. Part C is the probability of a year 10 student given that the person liked curry. So this time we're locked into the curry section. So total of 35, and there are 18 year 10 students. So that would be 18 over 35. And then finally D is pizza given it's a year 11 student. So again, locked into the year 11s. Pizza's 14, so 14 over 31. And that's all there is to it. Of course, you might also have to create your two-way table from the question. So I'll do that with the question I'm going to give you to have a go. Now, let's do this one step at a time. There's 75 members, so my total has got to be 75. 32 are adults. 32 are adults. That means we can do 75 minus 32, and that'll leave us 43, which must be teenagers. Of the adult members, 15 play badminton and 17 play squash. That's quite a lot of information. We didn't really need all of that. There are 22 teenagers who play squash and the rest play badminton. So 43 minus 22 gives me 21. And then we can work out our totals. So 21 plus 15 will give me 36. And then 17 plus 22 gives me my 39. And I always like to double check, 39 plus 36 does total my 75. So there is my two-way table done. All that's left now is to do the probabilities. So the probability that we have a teenager, given that they play squash, the same as the example, they play squash, 22 teenagers, 39 squash players. So 22 over 39. Probability it's an adult playing badminton. There are 36 badminton players, of which 15 are adults. And probability squash, given that they're an adult. So they're adults, 32 adults, 17 are squash players. So 17 over 32. And that's kind of all there is to it. Don't forget where you can simplify. Okay. Now, we've already seen a few formulae for our probability. What we're going to look at now is the remaining two. So these are the addition and multiplication formula. Now, the addition formula is simply the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. And this one's quite useful because, of course, you can swap this and this around quite nicely there. So you'd end up with, like, the probability of A intersection B is probability of A plus probability of B minus the probability of A union B. So, you know, I could swap this around and this could then... Sorry, you won't see that, but that was some terrible writing I just did. So a little bit of rearranging would also then give me this form. So this is quite a useful formula. Now, I was just about to do the multiplication formula, and then I thought you might not get why it's A plus B and then minus A intersection B. So let's just look at that for a second. If I have this Venn diagram, and I know what the probability of A is. Probability of A is, I don't know, let's go with 3 over 10. And we know the probability of B is 5 over 10, for example. Yeah? And say we know that the probability of A intersection B is 1/5, or I'm going to put 2 over 10 here. Then what that means is in my diagram, okay, that's 2 over 10 in there, which really means the total in here is going to be 3, isn't it? To get my 5/10, and the total in here is going to be 1 to get my 3/10. Yeah, total of 3, total of 5. That's kind of how it works, isn't it? Of course, I put these in as individual numbers, the total 10. We can easily put these as decimals in terms of the probabilities, or fractions as well, like 1/10, 1/5, 3/10, 2/5, etc. Now, if I look at adding the probability of A plus the probability of B, what you'll notice is that I'll do 3 plus 5, and I would have added this 2 twice. So when I do probability of A plus probability of B, I'm actually doing 2 lots of the probability of A intersection B. which is why I take away A intersection B. So probability of A union B, which is all of this, is probability A plus probability B minus one of the intersections as I counted them twice. And that's where that formula comes from. Get rid of that. Now, let's head back into the multiplication formula. So this is given in more than kind of one way. So the way it's often remembered is that the probability of B given A has happened is the probability of B intersection A over the probability of A. Now obviously this bit doesn't matter. B intersection A intersection B is the same thing. Okay, so this is what's happening. Now if you remember back again to the Venn diagrams, when I have a Venn diagram, what did we have just now? Something like this. Now when I have a Venn diagram, remember that when it's given that, so in this case B given that A has happened, what happens is we limit our probabilities to just the A. So it's over A, and the probability of B happening is this bit, which is the intersection. So it's a formal way of writing down what we kind of already know and already talked about in the previous video. And again, we can do a little bit of rearranging here, so we can get the probability of B intersection A is probability of A multiplied by probability of B given A has happened. Now this one, or in particular its rearranged form, is very useful for finding that intersection from information given to you in a question. And you will use this one quite a lot. This one you will also use, but I do think this one is the one you use the most. But again, you know, they are given to you. Well, sorry, I just wanted to double check. So what you're actually given in the formula booklet is you're given this one, which is great. You're given this one, but you're given it in this kind of form. Okay, just with the B and A's the other way around. But you're giving it in, no, you're giving it the same form as this. Yeah, but they write this B and A the other way around. Obviously this one doesn't really matter. But yeah, you're given this one. And then for there's a given that formula, which is one that I can't say I really remember using. Maybe it comes up in the odd question. Maybe it's just you don't need to use it. It's a strange formula. Have a look when you look in the formula booklet. I don't remember ever using it myself, but it's been a little while since I've done S1. Let me know in the comments if you've used that formula. Third one in the probability section of the formula booklet. So here it is. I actually just went and got it, cut and pasted it in. So this third formula, I can't say I've ever used it or really remember using it. So let me know if you've used this in class and what questions you've used it with. I'd be interested to find that out. So what I think we'll do now is a quick example with these two formulas, or formulae I should say, a quick question, and then I'll list all of the formulae and we'll go from there. In this example, we're given probability of C, probability of D, and probability of C union D. And we've got a list of probabilities to find. What I would say is in these types of questions, you'd use your formula to find this first one. And then after that, you'd be able to complete a Venn diagram, and I would use a Venn diagram then for the remaining ones. You can often use formulae to find your remaining probabilities, but in my experience, most candidates that do that either end up costing them in time or in mistakes. Some of you will be very adept at this and will be more than happy using the formulae, but a lot of you, I say a large proportion of you, will be better off moving to a Venn diagram as soon as possible in this type of question. So thinking about our formula, so we got the probability of A union B is equal to probability of A plus probability of B minus the probability of A intersection B. That's what it gives us. Obviously in this case it's C and D, so I want to swap out my values for my A and B's for C's and D's, so I stay in keeping with the question. So substituting our values in, we get 0.8 is equal to 0.55 plus 0.65 minus the probability of C intersection D. So probability of C intersection D is 1.2 minus my 0.8 is 0.4. And what I'd like to do now is take that and use it to complete a Venn diagram. So we've got C, we've got D, and this intersection is 0.4. Now we've got 0.55 for C, so this is going to be 0.15, and we've got 0.65 for D, so this is going to be 0.25. So 0.4 plus 0.15 and 0.25, that gives me my 0.8, which I didn't need to work out again because that was given to me. And that means that outside is going to be 0.2. And there I have my Venn diagram, which means that from here on out, it should be a lot easier. So part B, we want the probability of not C. So not C is everything outside of C, so 0.25 plus 0.2. As these are probabilities already, we don't need to think of as a fraction, so it's just adding them 0.45. Probability of not C, not D. Okay, so again, you get to one where you're a little bit unsure, so I just go with a quick little mini Venn diagram. Not C, everything outside of C, isn't it? Not D, everything outside of D. Intersection, where those two meet, and it's just all outside, so 0.2. Let's do D. Probability of C given D. So that again is very straightforward. Given D, so we narrowed it down to this bit, which means it's 0.65. And C within this is that 0.4. So this is what we're looking at. So we get 0.4 divided by 0.65. And that'll give me 8/13. Okay, so we narrowed it down to given that is D, and this is the C bit. Remember, like stuff like this, you can use the formula for, it's no problem there. I just think that the Venn diagram is the easiest way to go. So I've just noticed that this I've written E twice. Let's just change that to an F there. This is probability of C given that it was not D. So not D is everything outside of D. So if I think of my Venn diagram, now this is all we have left. Because if we not D is outside of D, which is only this section left, and which part of that is C, so 0.15. So this is 0.15 over my total, which is the 0.15 and the 0.2, you can see it here, So 0.35. And again, so 0.15 over 0.35, that gives me 3/7. Now, before we jump into the final part, part F, what happens if you didn't want to do a Venn diagram and you just use the formulae? So, part B, probability of not C is going to be 1 minus the probability of C. So 1 minus 0.55, so 0.45. Oh, that was pretty quick, wasn't it? Part C, the probability of not C intersection not D. This is one to know. This is the probability of 1 minus the probability of C union, D, which is 1 minus 0.8, 0.2. Of course, I'm trying to use the values that we are given. Now, part D, the probability of C given D has happened. This is the probability of C intersection D over the probability of D. Now, the probability of C intersection D is 0.4. We found that in part A, didn't we? And the probability of D is 0.65. So 0.4 over 0.65 gives me my 8/13. And then part E, probability of C intersection not D. So again, it's the probability of C intersection, this was the probability of C given not D. Probability of C intersection not D over the probability of not D. So the probability of C where it intersects with not D, again, this is kind of one that's really difficult without the Venn diagram, okay? Because you're looking at C and where it's not D. So it's that part of C minus the intersection of CD. So that's why it's the 0.55 minus your 0.4. Okay, because if you think about your C, your not D is everything outside of D, which only gives you this bit that's outside of D and in C. As this bit 0.4 will be in both C and D. And this is why the formula is a little bit harder. Not D, well, that's just 1 minus D, so 1 minus 0.65 there. So we got 0.15 over 0.35, which of course is 3/7. So there you go. You can do it with the formulae. In some cases, it's not too bad, is it? Some cases it makes you think a little bit more, especially like down here, where's possibilities for error. In part F, why are events C and D not independent? Well, we know probability of C is 0.55. Probability of D is 0.65. And probability of C intersection D is 0.4. Probability of C times probability of D is 0.55 times 0.65. And that is 0.3575, which is clearly not the 0.4. So therefore, probability of C intersection D does not equal the probability of C multiplied by the probability of D. So not independent. Okay, and job done. Now it's your turn. Now, this particular question I threw in there because it's very similar to one I've seen in more than one previous paper, although probably going back a few series now. So let's get into it. It's not too difficult, but once you've done it once, it's easy. If you didn't spot it earlier, we'll go through it now. So remember our formula, our addition formula. So it's A union B, so this is T union Q, probability of T plus probability of Q minus the probability of T intersection Q. Now what we're told here is that probability of T is the same as the probability of Q, and it's the same as 3 times T intersection Q. And what I want to do is make all of these a single one, so the easiest thing to do is to make it into intersection. So this is 3 times the probability of T intersection Q plus 3 times the probability like that, minus obviously my probability of T intersection Q. So what I've got is 5 times the probability of T intersection Q, and T union Q is 0.75. So that means that dividing by 5, the probability of T intersection Q is 0.15. Therefore, if I multiply that by 3, the probability of T is going to be 0.45, and the probability of Q is also 0.45. So from here now, we've actually found A and B within this. So we're actually on to C. So that's covered my A and my B. Now on C, probability of not Q. So 1 minus the probability of Q, 1 minus 0.45, so 0.55. Nice and straightforward. As I get on to D, again now it's either going with my Venn diagram or my knowledge. What I'm actually going to do is I'm going to pop the Venn diagram up here, because some of you might have already put this in. So we're at 0.15 in the center, 0.3 either side, and 0.25 on the outside. So for part D, we've got not T intersection not Q, so that happens on the outside, and 0.25. E, we've got probability of T intersection not Q. And remember now, if you get to one that's a bit funny and you're not quite sure, quick Venn diagram, don't need to put any values on. Remember, probability of T not Q now is outside of Q, isn't it? And remember, the direction is the opposite direction when we're doing these. So what you can clearly see here, shade this bit in red, is intersection. So where they meet is just in this part, which is this part, 0.3. Oh, wrong pen then, 0.3. And there we have it. Venn diagrams make your life easier for a lot of these probability questions. Right, what next? So obviously I know you've got the exams in a couple of days, so my aim to get tomorrow will be a short video on tree diagrams. As I say, it's quite straightforward, but I will just use the tree diagrams to show you where the formulae are, how you use them within the tree diagram. And I'm also going to do a, as requested, hardest questions from S1 video. I'll try and get both of those out tomorrow. Maybe one will come out, in the afternoon, and one probably in the evening.